So auditing data and answering that lifelong question isn't the end of the day yet. So what are we going to talk about in the next 40 minutes? We'll start off with looking at Nielsen's data architecture, and we'll really see how it had little fires going on everywhere, especially in regards to data arrival rates and data visibility. We'll start talking about the end of the day question, and we'll really understand that need for an auditing subsystem. We'll then go on into designing our auditing data. We'll store it, we'll query it, we'll maybe finally get an answer to that end of the day question, and then some alerts and add-ons, which are always fun. But first, who am I that is having a cold and is talking to you? So I'm Simona. I'm a senior big data engineer at ADOC based in Israel, but I was working for Nielsen Israel previously, so this is totally based on a true story. I love data. I've been dealing with data for the past decade now, which feels like a lot. I love music, the weirder the better, and I love traveling. So basically, this is me in a slide. Since we were doing this virtually, what I'm going to do now is just make a few assumptions about you lot. So I'm going to assume that you probably know your way around Spark, but this is really not very essential. I'm then going to assume that you probably know your way around Kafka. You're either a Kafka novice or you've been working with Kafka quite a lot. And so you know a lot of its pitfalls. And last but not least, you're curious about the end of the day question. So either you have no idea what I'm talking about, or if you encountered it, maybe you tried solving it or solved it. But if you've never heard about it before, don't worry about it. We're going to go deep into that question in the next 40 minutes. So let's begin. What you're looking at now is Nielsen's data architecture. So more than 50 terabytes of data, billions of events would flow through this architecture daily. And they would get collected first and foremost into the data serving infrastructure in our front-end layer. And at the time that this architecture was designed, we were running the front-end layer regionally. So we had several data centers all across the world, and each data center was running its own front-end layer, and so its own data serving infrastructure. So the data serving infrastructure consumes all of these events, enriches them, and then eventually produces them to its own regional Kafka. Now, it would be very important to mention that since the data serving infrastructure is that front-end layer that is dealing with receiving all of these events, SLAs are very, very important to them. So the data is being produced into that regional Kafka, and from there, it's being replicated using the replicator into the Kafka on AWS in our data layer. So our data layer and application layer are entirely on AWS. So that AWS Kafka, the data is being consumed from there using the data loaders. Now the data loaders are big, robust Spark streaming applications. They consume that data, just deserialize it, and just put it into our RDR. RDR, raw data repository, and that's just our data lake sitting there on S3. We then have our data processors, big, robust Spark jobs, consume that data, deserialize it, enrich it, aggregate it, and then eventually store it in all of these different data stores. So we have Druid, Postgres, MySQL, and even back into RDR. And each and one of those is serving its own purpose and its own application. And if we talk about applications, so we had several of these, BI, billing, data science, and they can consume that data all together through Hive or through each and one of these dedicated data stores. Now, before we begin exploring all of the pain points, I just want to mention a few things. So just a few points about our data model and Kafka infrastructure. So our one central Kafka on AWS was pretty big. We had 50 brokers, and all of our topics were not small either. So some of our topics were 750 partitions and some were 1,000 partitions big. We were using AVRO as our data model across all of our Kafka topics. And last but not least, we were using schema registry just to store that schema. Another point would be about our data lake. So each and every one of our topics had its own dedicated bucket in our data lake. Under each, we had daily folders. And so under each daily folder, that day's data was stored. And we would store all of our data just in Parquet format. So we were not using data lake or Iceberg or any other data versioning platform. We're just using Parquet. Cool. So this architecture really had little fires going on everywhere. And what we're going to do now is just start discussing all of these little fires, all of these pain points, so you'll really understand that need for an auditing subsystem. And so the first one I want to discuss, and the first point I want to zoom into, is this one. So what's happening here? Well, here we have the data that's just arrived right into our regional Kafka, and the data is being replicated using the uReplicator into our Kafka in AWS. Now, if you're not familiar with the uReplicator, it's a project made by Uber based off of Kafka's own mirror maker in version 1. What could go wrong? Well, aside from the most straightforward problem, like the uReplicator is crashing and data is not being replicated, some problems could be even worse. I've just mentioned a few moments ago that some of our topics were pretty big. Some of our topics were 750 or 1,000 partitions big. And just sometimes, the uReplicator would get stuck on some 5 or 10 or 20 partitions out of that entire topic. And so not all of your data is being replicated, but you're not even fully aware. Cool. So the next pain point I want to discuss is this connecting point. So here we have the data after it's arrived into our Kafka and AWS. So as I've already told you, we have the data loaders or Spark streaming applications, consuming that data, just spilling it as is into our data lake, the RDR. What could go wrong here? Well, again, the most straightforward problem. So our Kafka broker is crashing, our data loader is crashing, alerts popping up, bottom line, data is being late or just not arriving into RDR. And discussing all of these pain points, what didn't I actually mention? Well, I didn't actually mention how did we recover from all of these failures? And maybe even more importantly, what would be our criteria for recovery? Well, for this pain point, it would be pretty straightforward. So uReplicator crashing or uReplicator getting stuck, we just start the uReplicator back up again. So we could see that the data is being replicated again. We can see that it is being consumed. And at this point, we'd say, okay, problem solved. Data is being replicated again. And for this connecting point, we'd probably do something very similar. So Kafka brokers crashing or the data loaders crashing, we just start them back up again. Our Kafka cluster status is back to healthy. We can see that our consumer lag is reducing. So at this point, we'd say, okay, problem solved. Data is being consumed again. Data is being processed again. Everything's fine. But we didn't really know any of the implications that these crashes were having on our data integrity. We didn't really know if we had any duplications or data loss. And Nielsen's a data company, so data integrity is very, very important. And so at this point, I really want to start to discuss that end of the day question and why it's so important. And to get you to understand its importance, I really just have to take you to Nielsen's world, so to the media world. And what we'd want to do in the media world is count users. And we'd want to do that, we'd want to count their uniqueness on a daily basis. So if we talk a bit about aggregations, if you remember in our architecture, we have the data processor that is performing the aggregation, that is essentially performing that daily unique count. You'd want to run your processor only when all of yesterday's data has arrived, right? So if we talk about Monday, we'd want to process Monday, but only when all of Monday's data is already in your data lake. And the question is, when is that time? right? Because if you run your data processor too early, right, when you have partial amounts of data, you are going to run it on partial amounts of data, producing partial aggregations. And so you would have to run it again. In dealing with more than 50 terabytes of data, that would cost you quite a lot of money. So essentially, the end of the day question is, has all of my data, has all of yesterday's data arrived into the data lake yet? Can I run my data processor now? And so at first we tried solving this problem with a pretty straightforward solution. We said, okay, what time would yesterday would definitely be over? So let's say that 4 a.m., right? And so we'd use Apache Airflow for scheduler, and we just scheduled our data processors to run at 4 a.m. But then this one time we had a pretty big outage, we had a pretty big Kafka problem, and so no data was arriving into RDR. And so 5 a.m., 6 a.m., day definitely was not over yet. And so we were back to square one. And then someone suggested, hey, let's do something a little bit more complicated. Let's use the last time that a file was written to that days bucket as an indicator to as the day is over or not yet. So we used AWS S3LS as that indicator. But then that one time we had a pretty big regional outage. And so no data was arriving from a specific region. And so again, the indication was not good enough. And we were back to square one. And I think that if you look at Nielsen's architecture again, you really see what I'm talking about. So there's a problem. There's a problem with Kafka, or there's a problem with the data loaders. Essentially, data is being late to arrive to RDR. The data processors, not aware, they're consuming and aggregating on partial amounts of data, storing all of these partial aggregations in all of these different data stores, Druid, Postgres, MySQL, back to RDR. The problem is not over yet, because we have all of these applications, right? We have BI, reports, billing, data science. They're consuming that data and they're actually building their own data sets. They're computing their own calculations and computations on top of all of these partial computations. And so they would have to recompute their data sets as well. And so I think if you look at this architecture again, you'll really see how it had little fires going on everywhere. And so for both of these reasons, for just being able to understand all of these implications that these crashes were having on data duplications and data loss, and being able to answer the end of the day question, we've decided to design our auditing subsystem, Lifeline. And so what I'm going to do now is just walk you through the design of the data, our auditing data, which is really the heart of every auditing subsystem. Cool. So let's start off with designing our auditing metadata, our auditing window. So what should we keep in mind when designing our auditing metadata? Well, there are several points. The first one is that we had several Kafka topics. We didn't have one. And that number was not set either. So if tomorrow there's a new need and a new application, we are going to define a new Kafka topic. The next several set of points really have to do with the data serving infrastructure. And I've mentioned some of them before. So I told you SLAs are very, very important to them. Being that front-end layer of more than 50 terabytes of data, SLA is very, very important. They're written in Java, and each and every server is not running one JVM, but 2 JVMs. And so each and every process is working against a different set of topics according to its own configuration. Last but not least, about the data serving infrastructure is that we're not using just a simple Kafka producer, that we're using our own custom-made Nielsen Kafka producer. And this would actually make our job easier. Last but not least, in regards to the points that we need to keep in mind, is the use of AVRO. And this would actually just make our job a lot easier. So finally, what is a window? Why do we call auditing metadata an audit window? Well, if you talk about auditing data, you can't really audit forever. You are going to audit for a specific time frame, and you really need to keep that in mind. So auditing window just refers to that specific auditing time frame. We are going to configure it to 5 minutes, but if you write your code in such a way that it's configurable, it's not a problem to change later on. We never changed it. So taking all of these points into consideration, what would our auditing metadata look like? So our auditing window, our auditing metadata would look exactly like this. And I think you can see here everything we've just discussed. So for every topic, for every server, for every process, and for every window time, so for every 5 minutes, we are going to keep a counter. The counter of the messages, the number of messages that were being produced to Kafka. So essentially what's happening here is that we're identifying every single producer in this massive scale system. And for each and every producer, we're keeping a track of the number of messages being produced. And this is a metric that is not provided to us by Kafka. And you can see here before you just the AVRO definition of that auditing window. So we have the window start time, that's a window time, topic name, server name, and the window message count. If you're wondering where the process ID is, well, it's just part of the server name. It's incorporated in there, but that information definitely exists. So now that we have our auditing window, our metadata, we still need to be able to connect it to our actual data. So what we're going to do is we're going to create that complementary object. It's an object that's going to contain all of the complementary information that our data does not. So what our data does contain? Our data definitely contains the topic name, right? Because we consume from a specific topic. So our audit header is going to contain the window timestamp, right? That's just again, our window time, the server name, and the process ID. And if you notice the sequence ID in the AVRO in the audit header, that's totally fine, but it's a bit of a spoiler, and we're going to cover it a bit later on. So if we look at a very generic definition for an AVRO model, that would like a very basic topic for us, that what it would look like. So we have our model here, and we have a list of fields. And what we did, we've just added our audit header as a second field and just in the list of fields. Cool. So what we need to do now is just to be able to inject that information, inject that audit header into all of our topics, that have auditing enabled for them. And I have that the piece of code here for you. So what we're doing is we're just creating that audit header for every message, right? Just a reminder, our serving infrastructure servers are dealing with all sorts of messages and producing to different sets of topics. So we're creating that audit header in accordance to the message that we've received. We check the schema, we check and receive the audit header field that is being contained in that schema right now. And so what we do then is we check if the audit header field does not exist in that specific schema, maybe auditing is not enabled for it, then it's just fine. We're not going to include the audit header field. But if there is an audit header field, we're going to get its position, and then we're going to run it over using our own audit header that we've just created. And boom, that's it. So our audit header, our audit data is now part of our actual data. So in context of everything we've just discussed, we have all of our data, all of our messages just arriving in to the data serving infrastructure, and everything we've just discussed is happening right here. So we collect all of our data, we inject the audit header, increment the counter, and then produce our information. So let's talk a bit about producing, right? So our audit headers are just being produced as is, part of our data. What about our audit windows? Well, at first, we've just decided to produce them to their own Kafka topic. That was very, very tempting. But then we've actually noticed that we're auditing Kafka using Kafka. So that's a bit of a pickle. So what we did, we devised a very simple solution using Amazon API Gateway and a very simple Lambda that would collect that information, parse it, and store it in the same table that we're going to discuss in just a few moments. Cool. So let's talk about consuming our data. So if we first actually talk about audit headers, our audit headers are just part of our data, and our data is flowing through the same pipelines as it did before, right? So arriving to the Kafka on AWS, consumed by the data loader, spilled into RDR. So we have a very simple S3 consumer just consuming for every topic all of the audit headers that are arriving. And then for audit windows, we've just decided to keep both solutions as a backup for each other. So we have a Kafka consumer for a Kafka topic, and then that same Lambda if the information goes straight through the API. And so in context of everything we've just discussed, information is flowing into the data serving infrastructure is creating an audit window object every 5 minutes, right? And it's also injecting that audit header information into our data. And then the data is being produced, collected on the other side by an S3 consumer, by a Kafka consumer in the Lambda, and being stored in the very same table that we are going to discuss right now. Cool. So now that we know how our data looks like, sorry, let's talk about storing it and querying it. We've decided to use PostgreSQL as our database. Why is that? Well, first of all, the data is structured. Data is definitely structured, and we're not going to keep a lot of our data, right? Because if we talk about auditing data, it's very similar to log data in the sense that you'd probably want to look maybe at a month or 2 months back, but nothing over that. And then the data is very, very structured, and you should know that by heart right now, right? So we have for every topic, for every server, for every process ID, for every window time, we're keeping a counter of the number of messages that are being produced. So in order to design our table, though, we first thought about the questions that we want answered. We want these questions answered regardless in different levels of granularity. Some of these are given, right? So topic, server, process ID, window time, but some of them are not. So, because what about region, right? We don't have region in our data, but we probably want to know all of these questions, all of these answers in regional granularity, because we did have a lot of regional problems. And then what about arrival rates? So arrival rates, that's pretty straightforward. How much of the data that is being produced actually arrived into RDR? And then we have arrival rate of the latency. So that's a bit less trivial. So how much of the data that was actually produced arrived within an hour or 3 hours or maybe a day? Cool. So with those questions in mind, let's design our table. And I think you'll really see that we have everything that we've just discussed. So our table is going to have an audit timestamp, a topic, a server, a process, an event count column. It's also going to have a location column. So our location column is just a representation of the origin of the data. Did it arrive as metadata? Did it arrive from the data? So we've just we've kept this column because we always thought that we'd want to add more locations in the future. Maybe we'd want to collect our data from Kafka and not from the RDR. Cool. And what about some other add-ons? So we've added a region column. We've actually parsed it from the server name. It's not best practice, but it was the quickest way to go. And then we also added an insert time. So using insert time, you can just calculate the arrival latency, right? So you have insert time and you have the audit window timestamp. That's the time that the data arrived into the table versus the time that the data was actually produced, just deducting it one from another, and you get the arrival latency. Cool. So I have an anonymized version of this table here for you today. Some interesting points to touch. So we have the insert time and window timestamp. I really want to draw your attention to the fact that all of these times are in UTC. We had developers sitting in Israel, we had developers sitting in the States. So just keeping all of these times standardized in UTC was very, very important to us. So we have topic name, right? Just several topics, server names. You can see that the region just got straight from the server name, different processes ID. What I really want to draw your attention to, though, is the event count. So you can see that some event counts are pretty high, some are not. But we can see that we have event counts of 0 here. How is that possible? Well, if you look closely, you will see that the rows with an event count of 0 are the ones that have a location of Kafka windows. So what's actually happening here is the fact that the auditing subsystem is working all the time. Even if that specific server, even if that specific process is not receiving any traffic whatsoever, the data auditing subsystem is going to keep working. And so it's going to keep producing these auditing windows, right? These auditing metadata objects. And so our Kafka windows location is just a representation of that. So that event count of 0 is just an indication that the auditing subsystem is working. And so I think that's pretty cool. So what you see before you now is just a logo for Apache Superset. And that's a tool that we were using for all of our BI needs. And that includes that auditing, the auditing data. So some cool charts here for you today. So we have the data arrival latency. You can see the data arrival within 3 hours for the last month. And you probably noticed that that number is a bit higher than 100. So yeah, we did find some data duplication and some data loss in our data, which is very, very important. And so just straightforward data arrival rates for the last 1 hour, for the last 24 hours. And then this very, very simple query. So this query is the one that's calculating the arrival latency. So you can see what we've discussed before. You can see that we have the window timestamp that we're deducting from the insert time. And just this way, we're calculating that arrival latency. Just calculating the number of messages that actually arrived within that interval of 3 hours. Cool. So what you see before you now is, again, the logo for Apache Superset. And we would see this logo quite a lot because this is the logo that Superset shows you while it's actually loading data and running your queries. And at this point, I just want to do a small shout out to my dad. My dad, who is a DBA and a developer, and has been for more than 30 years than me. And when I came to my dad with a query that was running for over a minute, he didn't give up until it was running for just a few seconds. So thanks, Dad. So how did we do it? How did me and my dad actually optimize that PostgreSQL table to run for all of our auditing query needs? So the first thing that we did was just weekly partition that data. And I say it with a lot of ease, but if you've worked with PostgreSQL, you probably discovered that just automatic partitioning is not as simple. So we did have to, just like keep that in mind, we did have to create a few DAGs in Airflow, or just orchestrate a few processes that would create these partitions on a weekly basis. We, of course, created all of the primary and complementary indexes according to the predicates of our queries. We've created a job that would offload that old data to history. So I've told you before that your users or you would probably just want to see a month or 2 months back of auditing data, but we don't like, as big data engineers, we don't really like throwing that data away. So just consuming it, aggregating it, analyzing it, and storing it away. That was the way to go. Just a few points about working in parallel while using PostgreSQL, specifically RDS on AWS. So I really encourage you to read about those 3 configuration variables on the screen before you. So the max worker processes, the max parallel workers per gather. You would be really surprised as to what 10 workers instead of 1 can do for your query. That's amazing, working in parallel. And then, last but not least, just treating the optimizer. I know that we all think that the optimizer knows best, but you'll be really surprised as to what a union can do instead of an in predicate for your query and for that runtime of that query. Cool. So we really understand how that auditing data looks like. We've stored it, we've queried it. Now let's see if we can actually get an answer to the end of the day question. And I have a pseudocode with all the things that we need to check here for you. So the first thing that we're going to do is just check the validity of the input parameters. But no, I'm just kidding. We're not going to do this. I'm not going to put you through this. What we're going to do is just understand the 3 basic questions that we need to have answers for in order to get the end of the day question. So the first question that we want answered is the data arrival rate for the entire scope. Why? Well, basically, if the data arrival rate for the entire scope is not above our threshold, then the day is definitely not over yet, and we can finish now. But let's say that the data arrival rate for the entire scope is just fine. Yes. So the next thing that we want answered is the number of audit windows for the entire scope. Why would we want to do that? Well, let's say that there's a problem with the auditing subsystem, and so it's not actually producing auditing windows. That would be a problem. So we're going to check for the number of audited windows for the entire scope to check that the auditing subsystem was actually working for that time frame. Okay, so let's say that the data arrival rate for the entire scope is just fine. Also, the number of audit windows for the entire scope is just fine. We still want to check the arrival rate for that very last window. Why would we want to do that? Well, if I take you a few slides back, when we were looking at the Superset charts, we saw that some of the arrival rates were a bit higher than 100. When you see these numbers go above 150 or 180, you know that you definitely have a problem. And let's say that it went over 180 at some point in the day, and it didn't get fixed yet. So we had a really high data duplication. That data duplication arrival rate would actually create a skew in your calculation. And so if you had data arrival duplication and then data arrival loss, it could actually trick you, right, while calculating the data arrival rate for the entire scope into thinking that the day was actually over, but it is not actually over. It's just very duplicated and very skewed. So what we're going to do is we're just going to check the arrival rate for the very last window as an indication to whatever the day's actually over or not. So the data arrival rate for the entire scope is just fine. The number of audit windows for the entire scope is just fine. And then the arrival rate for the last window is A-okay, then yes, yesterday's finally over. Yes. Cool. So what we did, we've just devised a very simple API for our developers, for our big data developers, so they could use that in order to get an answer to that end of the day question. So just using Apache Airflow scheduler, just same as before, we would send a question to our API, and our request would contain a topic name, right? So for a specific topic, for a specific scope date, and for a specific threshold, please tell me if the day's, please tell me if the day is over yet or not. And if it's not over, please give me the reason. Cool, so we're at the very end, and at this point, let's just start discussing alerts and add-ons. So what did we do as alerts and add-ons? Well, we actually managed, just using all of these data and just using the API that we've devised, to create an alerting system. And we created alerts in different levels of granularity, just as we wanted, on region, topic, and server. And I cannot stress enough how important these alerts turn to be, because these alerts were popping up faster than any of the heartbeat alerts by Spark or Kafka. And not only that, but these alerts actually helped us in just understanding where the problem is. Because if you get an alert on an entire region, you know that the problem is probably not with Kafka or with your data loaders. It's probably with the U replicator. And if you get an alert on an entire topic, you know that the problem is probably with the data loader and it's not with the replicator or with Kafka. So just using these alerts helped us solve all of our problems, all of our crashes a lot faster, and just help us understand and just raise the bar for the criteria as to the problem's over or not. Then the other thing is detecting duplications. When we looked at the audit header, you noticed that it was written SequenceID, and I've told you, we're going to discuss it later on. It's a bit of a spoiler. Well, we're going to discuss it now. When we looked at the Superset charts and we saw that some of the numbers were a bit above 100, when we saw that, we were like, well, there's not a chance that we have actual data duplication in our system and in our data. There's probably a bug with the auditing subsystem. So what we did, we decided that just to add a running SequenceID to all of our audit headers. So every audit header for every window, right, for every window would get a unique SequenceID. And in that way, we were able to detect duplications. So hence, there was actual data duplication. The problem was not with the auditing subsystem. Because the data is in Parquet format in S3, you could just use this query, use Spark SQL, use any other way you'd want, just aggregate that data on the window timestamp and the server name, and just get the number of sequence IDs in it. Because if the sequence ID count is higher than 1, right, if there is a window where the distinct sequence ID is higher than 1, then there is actual data duplication within that window. And then last but not least, locations. You saw the table, there was a location column there, and it was just differentiating between windows, right, between our audit windows that we collect from Kafka, so Kafka windows, and our actual data from RDR, so that's our RDR headers. But our architecture was so robust, it had so many pipelines, so many steps in that waterfall, that we always thought just about adding more locations and collecting that auditing information from more steps and more points. And that's why just like more locations was our main goal for the future. And with this, my presentation is done. I hope that you've enjoyed it, and feel free to approach me on any social media and ask questions. Hopefully see you next year.